All right, here we go, kids. Here's our first objective in the gas law. This is the one we really need to get to. And this one's going to deal with the combined gas law. All right, so the combined gas law explains the relationship between volume, pressure, and temperature. All right, so the reason why it's called the combined gas law is because it's a combination of three laws. One is Boyle's. Boyle's law deals with pressure and volume. So the initial pressure, which is pressure 1 and volume 1, will equal pressure 2 and volume 2. All right. As long as you have like units for these, the calculation will work. All right. And this is an indirect relationship. So as pressure goes up, your volume should go down. Should. Indirect relationship. All right. So that's your first part of it. Second part of it is going to be Charles' law, and Charles' law deals with volume and temperature. All right. So your initial volume, volume 1, your initial temperature, temperature 1, is equal to your secondary or final temperature, final volume, and your secondary or final temperature. All right. There is a trick to this. Make sure the volume's all in the same calculations. We usually want to convert them to liters, but not always. But temperature always needs to be in kelvins. So what this law tells us is that as volume goes up, temperature will also go up. All right. So usually for pressure, usually we want it to equal to in atmospheres, which is a pressure measurement. Volume, we usually want it to be in liters, usually. And volume in this case, again, in liters, not always, but it's a common unit that we normally use. But temperature, this is the important one. Temperature is always in kelvins. So if there's one you got to remember for right now for sure, for this part, is temperature is always in kelvins. All right, so make sure you look up that formula, which I believe it's kelvins is equal to 273, I think 0.15 plus your degrees Celsius. All right, but double check that. I'm pretty sure that's right. And then Gay-Lussac's law deals with pressure and temperature. So my initial pressure and my initial temperature, pressure 1, temperature 1, is equal to my pressure and my temperature of the second part. So what this law tells us is that as pressure increases, my temperature should also increase. Another direct relationship. And again, pressure should be in ATMs, volume and temperature always needs to be in kelvins. All right. So we combine these three equations, and here's what it looks like. We have PV over T, all initial, all what you're starting with, PV over T, secondary, and all you do when you get a problem is basically cover the one up that you don't have. Like for example, they might say you get pressure and you get a temperature, but they don't get any volume. Well, then don't worry about it. Don't include your calculations. Just take it out. All right. So it's just really plug and chug. All right. Plug it into the appropriate variable. Do the calculation. All right. And from before, hopefully remember this. Pressure is a measurement of physical force of the molecules around you. Volume is a measure of the space it occupies, and temperature is a measurement of the average kinetic energy of a particle. In other words, the average movement of particles in an area. So let's take a time and let's try a sample problem. So here's the formula we're going to use, right up here, and we're going to do these two sample problems. So a 1.3 liter, L is liter, balloon is taken from room temperature, which is about 25 degrees Celsius, and placed into a freezer at 11.5 degrees Celsius. What's the new volume? Well, I have my initial volume right here. So that would be 1.3 liters over my initial temperature, 25 degrees Celsius, but we don't want 25 degrees Celsius. We want that to be in kelvins, so add 273 to it. So that gives you what? 298? Yes, I believe so. So then you go 25 plus 273, and if you want to get technical, 0.15. So that'd be 298.15 is equal to, so these are my initial volume, my initial pressure, right up here. Initial volume, initial temperature. Notice how they didn't give me pressure? I don't even worry about it in the calculation. I just don't include it. And then I don't know I'm trying to find my next volume, so I'm trying to find volume 2, which is my x, solve for that variable. But they give me my last one, my last temperature, which is 11.5. So 273.15, so that would be what? 284.65. I believe that's right. Then you solve for volume. So just plug and chug. So because we're dividing with this side, you're going to multiply to that side, and you're going to solve for volume. So volume squared. So my secondary volume, punch it in my calculator. Let's see what we get here. 1.3 times 284.65 is equal to 370 I got, divided by 298.15 is equal to, and I got a volume of 1.24 to round it, and this is going to be in liters because this one was in liters as well. So here is my calculation. All right. And technically, if we're going significant figures, it should be 1.2 because this one has 2 significant figs, this one has 5, that one has 5, and you always, when you're multiplying and dividing, you always go by the lowest number of sig figs. So this one should be 1.2 actually. And that's how you figure it out. Just plug it in, chug it out, and this is going to match that label because they're like units. There it is, plug and chug. Let's try another one. Now we have 12 liters sample of NO2 gas at STP. What would its new volume be if the pressure was decreased to 575 millimeters and its temperature was doubled? All right. So we got a lot of stuff going on here. So I know I have 12 liters to start with. Okay. 12 liters. And I'm trying to find, let's see, the initial pressure at STP should be 1 atm, right? Remember, STP, standard temperature and pressure, is 0 degrees Celsius and 1 atm, I believe. Correct me if I'm wrong, but I think so. Hopefully I'm not doing this problem wrong. So 1 atm, which we'll talk about later, is equal to 760 millimeters of mercury. So I can just take this and convert, so it's at 760 millimeters of mercury. And my temperature, I believe, is it 0 degrees Celsius? 0 degrees Celsius, which is 273 Kelvin, which is what we want. Okay, now, there's all my initials. Now, what would the new volume be? So I don't know the volume, don't know that. If the pressure decreased to 575, whoops, and the temperature was doubled, so 273, well, everyone's like, the temperature was doubled, so obviously it would be what? Oh boy, 273 times 2 would be 546 Kelvin. Solve for your secondary volume. So let's solve for that. Clear it. 12 times 546 times 760 is equal to a very big number divided by 273, and then also divided by 575. And I got about, for V2, and this is my calculator did it right, 31.7 liters. Okay, it should be liters because this is in liters as well. All right, so really all this whole thing is just plugging and chugging. All right, use your equation, use this combined gas law equation. Whichever ones you don't have, don't include in the calculation, and solve for the one you don't have. All right. So remember, liters is going to be a volume calculation. Millimeters of mercury, atmosphere, PSI is going to be a pressure, and then temperature is going to be in Celsius, but you always want to convert to Kelvin so you don't have any negative numbers. All right. Hope this video helped. We'll talk to you guys soon.